So, this is the title, a bit provocative, of course. So, this is my email. You can contact me at every time, of course. So, just some background on the science and technology. So, some milestones. So, 45 years ago, man went on the moon, so it was of course a very huge challenge and a giant leap for mankind. Everybody knows this picture. Now a robot is crawling on Mars, the red planet. So far away, it takes 20 minutes for the signal to reach us. So it's really far away. And sharing odors with friends over the web is still science fiction. This is crazy. Yes? Okay, so let's enter in the history. So about the sensor digitalization, the first sense is hearing. We have a lot of receptors in cochlea. We are sensitive to tactile vibrations under 20 Hz. And these are the main characteristics. Mostly a very wide dynamic range, 120 decibel, so it's 2 to the power 40. So it's very, very large. So we know, of course, how to record and to playback sounds. So the first analog device was the phonograph. It's quite old. Digital recording began with the compact disc in '76. And of course, we have a lot of devices, home cinema, phones, and so on. This is a nice picture, isn't it? I love it. And we are able to reproduce very faithfully, thank you. We are able to reproduce very faithfully the sounds with the same dynamic range and with a very, very low distortion. Vision. Vision is a dominant sense for human. This is our principal sense. So, well, we have three types of color receptor, RGB, you know. We have also black and white receptors, which are very, very sensitive. And we have the spatial encoding, means we have the stereo vision, so we have the 3D vision. And the sensitivity is excellent. 1 photon is really nothing. We know how to record and do playback. So analog photograph is 1892 by Nicephore Niepce. But this is not, of course, a high resolution picture, but this is the first picture. Of course, the cinematograph with a quite good quality for this time. This is the first, not really the first film, but the first commercial film. I mean the film that a lot of people viewed in cinemas. You have everything from the cinema in that movie. All the sequences, a lot of characters. Digital recording, the CCD device was invented in '69, and the Laserdisc, it was not the DVD, so before the DVD, Laserdisc, so it was analog recording in '72. And it's very, very easy to deal with the colors because we have primary colors and we have color spaces. So with the three primary colors, you can really make every color you want with all the intensity you want. It's very, very easy. Okay, and for the coding, we have 1 billion colors, so it's very large. Well, in this single picture, you have close to 100,000 different colors. While transmission, you know, just to recall, so the first transmission were wired over phone lines, then the Ethernet, optical fibers now for the wired, and we have also the wireless. The first one was the broadcast for radio and then for TV. Then Wi-Fi and WiMAX. Then for the phones, 3G and 4G. And what is interesting, we have a lot of international norms made by INR, and we have MIME types, mean that we have norms for every kind of multimedia information you want to transmit. So for still imaging, sound, movies, and so on. You have norms for everything. Up to now, we have not norms for others, of course. So, olfaction. Analog storage. Well, what for you? What is the time analog storage of odor was invented? Do you have any idea? I mean analog storage. No idea? It's very, very, very old. It's really from ages. The first device was made with a horse bone, which has a lot of capillaries inside, so it's porous. And this device is still in use for ham, mostly for Italian prosciutto and for Serrano in Spain. And this manner of sampling is included in the specs of the Parma prosciutto. Now, so it's still in use now. So the bone is introduced into the ham and then sniffed by experts. Then after we had absorbent polymeric traps, so in the 60s, which were mainly used for GC applications, and they are thermodissolved. But in that case, no duplication is possible. So you have one device, one sample. And if you want another sampling, you should use another device. Digital recording. Well, everybody knows e-noses and gas sensors. So now we will quit technology for science. E-noses, the fundamental is very, very simple. You have a sample, you have gas sensors, electronic data acquisition board, a computer, and then from a headspace, I mean the aroma are generated from the sample and reach the gas sensor. And then, of course, you have a decision, is accept or fail. This is very, very basic, but of course, inside the black box is a bit more complicated. Well, we have a lot of available sensors that we can use with that electronic nose. Well, I will not enter the details. If you want some more information, I can, of course, respond to your questions. The electronic nose. So it's commercially available for 20 years. This is not a coffee maker. This is, no really, it's an electronic nose for Nordic sensor technology. So it's available for 20 years. I began working in that field in 93, so I'm quite old now. And the problem is now time to take stock. So it was marketed as a general purpose instrument, but there are very, very few commercial applications now. And I don't know one application in the food industry after 20 years. So of course, we have to raise some questions. So we are still seeking for the killer application, I mean mass markets for the people who manufacture this device, but unfortunately, we are not rich. So the question is it a problem of gas sensor? No, we have good sensors, but maybe there is a missing link with the human. So we will speak about human olfaction now. Just an example to show you how complex is the task. Everybody knows wines, of course. Wines contain a lot of chemicals. For example, Chardonnay wine is a white wine which is produced all over the world, in Europe, in Africa, in South America, in California, everywhere. And more than 1,000 chemicals were already identified in that wine. It's a lot. Of course, wine contains alcohol. I mean, a lot is not ppb. It's really a lot. And what we call the bouquet, so it's really what makes the typicity and the cost of a wine, is due to trace compounds. Just an example for the core tent. Everybody knows the core tent odor of a wine. It's due to trichloroanisole, and which is present at sub-ppb level. So it's very low level. And we are not able to access this level with sensors. And we have a strong influence of everything that is in the wine: polyphenols, sugar, acids, and so on. So from our experience, we have 30 years experience in the food analysis in my lab. It's impossible to classify wines on criteria, aroma criterion using GCMS, which is the most powerful technique up to now. So wine recording is really challenging. Just an example of what is inside wine. So I will show a GCMS of a wine. So it's not the complete, because it's from time 5 minutes to 65 minutes, but indeed the length of the chromatogram is that one. So it's just one part. And we will focus on one small part of this sample. This wine is described oxidized by a sensory panel, so by humans. So just make a close-up of this region. So it's really a small region. And this is the normal sample, standard sample, and this is the oxidized sample. And what you can see, the difference are in the blue zone. And the chemicals are the same. In both samples, the chemicals are the same. What is changing is only the ratio between these chemicals. And these chemicals are really a very, very small zone there. So if you want really to discriminate two wines by GCMS, it's not possible to do that with a computer. Only human can do that and focus on that molecules. So if you want to do that with an electronic nose, good luck. So again, the electronic nose, we have to learn from humans. I like this picture. So olfaction, I mean human olfaction, not digital olfaction, is a very complex process. So forget this, it's a human process. So we should take care of the human sampling and understand the human process. So human olfaction, I will not enter the details because it may last three hours, just some indications. So we have already mentioned trichloroanisole, so the cork-10 odor in wines. The two other chemicals, well, doesn't work. The two other chemicals are earth odors and iron odors. This is strange because these chemicals can be found either in wines and in tap water. It's the same chemicals. And the detection threshold is very low, 10 to the power minus 14. So it's very, very low level. We have the Stevens slope, which is a logarithmic law, which is very common to all sensory senses, human senses. It's equivalent to the Fechner law for audition. And one other problem is that this is not monotonic. I mean that the edenic tone, so what you call odor, depends on the concentration. So for one chemicals, if you have different concentration, you will get different odors. So this is complicated. So this is the human perceived intensity for two different chemicals. So the first zone is the initial zone, so the threshold. The second zone is the dynamic zone, so usually we are working in that zone. And the third one is the saturation zone. And about mixture, because usually we are dealing not with pure chemicals, but with mixture of chemicals. This is very simple. Nobody is able to predict the odor tone for any mixture. It's impossible to modelize. So again, olfaction is a very complex human process. Because indeed, odor doesn't exist. Odor is just a brain concept. It's a neuron signal processing from a chemical vector. So you have chemicals or a mixture of chemicals that come to your nose, to your epithelium cells, and then go to the brain process, and then you get the odor. But what an odor, say, of cocoa or whatever you want, is not the same for me and for you. It's really a cultural concept. So we use very frequently sensory panels. We have a very high number of sensory panels in our lab, so which provide individual odor description. And the vocabulary comes from Hans Nobel aroma wheel. You have the web links if you want more information. There are hundreds of basic odors. This is an example of this wheel. This wheel is for wine. You have also a different wheel for coffee, for cheeses, whatever you want. You have same odor families. This is woody, this is earthy, this is fruity. And if you enter the details, woody, you may have burned, phenolic, resinous. And again, you can have bacon, phenolic, oak, cedar, smoky, and so on and so on. And in chemicals, you may have chemical sulfur, sulfur dioxide, pungent, petroleum, diesel, kerosene, and so on. So you have really a lot of possible. Okay, I will not cite all the others. For fruity, you may have tropical fruit, berries, and so on. So you have really a lot of odor description that are common to a sensory panel. I mean, all the people in that panel use the same terms to characterize one odor. Okay? So the problem is that we have no primary odors as we have primary colors. So with three fundamental primary colors, you can get every color, every picture, every movies with an excellent definition. But with odor, you can't. So we do olfactometric measurements, again, on humans. So we conduct studies on odor mixture. This is an olfactometer in our lab that can mix up to 8 different chemicals and send to a panelist's nose. This system is very huge. It's my size in 8, more than my weight. And usually we work on binary or ternary odors, because if you mix 8 odors, really it's impossible to deal with that. And it's used to tune a mixture to reach what we call the blending harmony. Do you know what is blending harmony? Okay. So maybe I will explain a bit. And out of this harmony, the perceived odor is totally unpredictable. So you will have more information in the afternoon during Charles Penn's lecture. So what is a perceptual odor blending mixture? This is very simple at all. I mean, the principle is simple. Okay, this is this chemical, ethyl isobutyrate, which is close to strawberry odor. Okay, it's not strawberry, it's close to. And if we compare with the pineapple typicity, it's quite low, it's about 30%. If you consider ethyl maltol, which it's close to caramel odor, well, it's about 30%, so it's less close to pineapple. If you consider allyl-alpha-yanone, which has an odor of violet, the flowers, well, it's about 25%, so it's less. But if you mix all these different chemicals, you get a mixture that is closer to about 60%. This is close to pineapple odor. The problem is that this mixing should be very, very precise. I mean, more than 5% of precision for the different amounts of the chemical. If you have out of this precise mixture, you have another odor that you can't predict. Okay, let's come back now to the history of senses digitalization. So now for olfaction. For the aroma odor playback, so analog playback, it's olfactometer. So these systems are used only for research purpose because they are very, very expensive. They require highly qualified people to work and a lot of panelists. Odor generators, well, now there are a lot. One of the first that was commercialized was made by Indigo. This is a scheme of this. Now we have a lot of olfaction displays or shooters, so you will see during the demo, but we have a limited range of odors. And again, we have no primary odors. So it's very difficult and risky to predict what will be the resisting odor of a mixture. So the bottlenecks is that you may have shooter memory effects, and the memory effects will be different for every chemical. So some will last more time, will remain trapped into the system for a longer time. Time intensity management is very, very difficult because the odors of a mixture varies in time, because all the chemicals don't have the same pressure vapor. So the time intensity of each chemical is different. And the odor plume is very complicated. This is the 2D representation of an odor plume. The more red, the more intense the odor is. And you can see that it's really unpredictable.
What do you mean by to manage? To manage spatial diffusion?
If I send an odor to you, I'm not able to manage what will be the plume in this room. If I want to send to you, maybe another people will get more odor than you. And again, we have no primary odors. So it's impossible to predict the odor of a mixture. I'm really insisting on that because this is very, very, very important. And about what we call Grand Cru, in this case is coffee. I think you know this kind of coffee. You have, I didn't really count, about 20 different coffees, which every coffee has a different odor and a different aroma, and they are very different. But if you want to analyze them, or if you want to reproduce them, you will not be able. Because the difference, or what we call the bouquet of one Grand Cru, is ppb level. So the difference between the two caps are really ppb level. So if you want to analyze, or if you want to play back, you will not be able to do that. So indeed, sending odor is not really a novel idea. The first were sent with film, so in 1929, so it's quite old. This movie was perfumed from the ceiling, and it lasts 1 hour to recover the basic odor of the room. After another trial in 58, so it was a cotton wool perfumed with rose oil and diffused by a fan for the Rose Bowl game. It was a newsreel. After, we had two technologies that were fighting together. So it was smell-o-vision and aroma in 59, so you can see that is quite old. And they had 100 different aroma they diffuse in the air conditioning. And the movie was Behind the Great Wall. It was an Italian movie. But again, with the air conditioning, it's very complicated to manage the odor plume and to manage the recovery. And the telesmell is not recent too. The first proposal was for Pacific Northwest in 1998. And then after, we had the Exalia project in 2003. Okay, so of course, it's a very, very exciting challenge. Just imagine George. I think everybody knows George. Okay. Really, with a coffee aroma plume around him during this ad, and of course, the power of this global ad will be increased tenfold, at least.